Hello again. Welcome to one of the really big stories in science. It's so big, in fact, that I'm just going to take a moment to put it in context, so you get the full flavour of just how important this work is. The Greek philosopher Aristotle was one of the most influential men who ever lived. His teachings dominated science for 2,000 years. Teachings like, the Earth is stationary, and it sits in the centre of the universe. Heavy things fall faster than light things. And a particularly tricky one. If you want an object to keep moving, you've got to keep pushing or pulling it, like a horse and cart, for instance. These deeply flawed ideas were eventually challenged by brave people like Galileo. But we had to wait until the end of the 17th century for the book that changed everything. In his masterpiece, the Principia, Isaac Newton swept away centuries of confusion and muddled thinking, and replaced it with our first clear and comprehensive explanation of how the world works. With his three laws of motion and his law of universal gravitation, Newton laid down a body of knowledge that we still use today. With the help of our friends from PhET, I'm going to run through Newton's three laws of motion, and if you're ready, we'll make a start right now.
So here I am, with a large wooden crate that has to be moved. At the moment I'm standing on a displacement axis, and we'll take all our vectors to be positive in this direction. Okay, so let's have a look at the crate. It doesn't look like it's doing very much at the moment, but it is in fact obeying Newton's first law. Any crate will continue to do what it's doing forever and a day unless some unbalanced force comes along and makes it do otherwise. That's Newton's first law. It's sometimes called the law of inertia. Inertia is simply the tendency of an object to resist change. And the bigger the mass of the object, the bigger its inertia. So, are there any forces acting on the crate at the moment? Well, yes, there are. Just stop and think for a moment and see if you can work out what they are. There they are. Fg, of course, the force of gravity, that's the object's weight pulling downwards. It's measured in newtons like all forces. And balancing that force is an upward force supplied by the wooden floor. Fn is called the normal reaction force. So at the moment, the crate is in equilibrium. I think I need to add some more forces to make it a bit more interesting. Let's try that. Nothing happened. Try again. Still nothing happened. What do you think's the problem? What am I doing wrong? Let's have a look at the force vectors again. There we go. Friction, FF, fighting against me. I'm going to push a little bit harder, and this time let's hope for some success. I'll just stop it there for a second. And you can see that the four forces on here no longer balance. The applied force, Fa, supplied by me, is bigger than the friction force. And we have an unbalanced force at last. I can show you that. The green arrow that's just appeared can replace all four of the other forces. It's the sum of all the forces, it's the unbalanced force, and it's that force that caused the crate to do something different. It started to move. So friction is the thing that makes everything else more complicated to understand. It's this problem that held back Aristotle and all the people that followed him. So what if we could remove friction altogether? What kind of experiment would we have then? Here we are in the ice lab. I've replaced the wooden floors by ice, and so friction has disappeared. I'm about to supply an unbalanced force to the crate. What do you think will happen? In particular, what do you think you'll see on the velocity time graph? Okay, here goes. So, I only supplied the force for a brief instant, but it brought about a change. This time the crate is moving across the screen, as you can see, with a constant velocity. This is the second aspect of Newton's first law. If an object is moving, it will continue to move in a straight line at constant speed because of its inertia. Here's Newton's first law restated. An object at rest will stay at rest, or if the object is moving, it will continue to move with a constant speed in a straight line forever, unless an unbalanced force acts upon it. I'm just going to have a little fun now and push the box across the ice. I'm going to give it a few nudges. What do you think will happen? And again. And again. As you can see, each force produced an increase in velocity, but once the force was over, the box continued to move with constant velocity. Now I've moved to a bigger ice slab, but still no friction. As we've seen, Newton's first law explains what happens when all the forces acting on an object are balanced. But now we're going to examine in more detail what happens when the forces on our object, a filing cabinet this time, are unbalanced. This is covered by Newton's second law. This useful little diagram is called a free body diagram, and it summarises the forces acting on our filing cabinet at the moment. They're balanced, of course. But when I start to push, that will change. Remember, there's no friction in the ice slab. Watch. Here's the applied force. As we can see here, it's an unbalanced force. And as the vertical forces cancel out, it is in fact the total force acting on the cabinet. And we can simplify that in the diagram. Now we're ready to go. When I press the button, the unbalanced force will have its effect. I'd like you to predict the shapes of the two graphs, the force time graph and the velocity time graph for this simulation. I want you to predict what happens all the way across until it hits the wall. Remember, the force will be applied all the way across the screen. Okay, if you're ready, let's go. Slow start. That's inertia again. I'll just pause that. So the applied force, so the total force, was constant until the cabinet hit the wall. Then there was a huge force in the negative direction, which brought the whole thing to a standstill. If you look at the velocity time graph, it's probably what you expected. Slow to get started, but there's a uniform increase of velocity over time, indicating constant acceleration. We can look at the acceleration time graph too. You can see something very interesting here. The shape is very similar indeed to our total force graph. In fact, it looks as though the force was responsible for the acceleration in this case. We need to investigate this further. Okay, we're still in the ice lab, but this time I want to change the forces systematically, so I'm looking for a pattern. Let's see what happens. I've set this on 100 newtons and it's paused at the moment, ready to go, so let's go. Slow and steady, that's the inertia again. But you see the velocity is increasing, let's pause it there. What do you think will happen if I step up the force to 200 newtons? Right, let's try. As you would probably have predicted, the velocity starts to increase faster. So let's double the force again to 400 newtons and let's see what happens this time. We need to look at the acceleration graph. As you probably would have expected, the acceleration graph mimics the force graph yet again. Let's do a playback. 0.2 meters per second acceleration. It doubles. And it doubles again. So every time we double the force, we double the acceleration. That's a directly proportional relationship. Beautifully simple. Double the force, the acceleration doubles, as long as the mass is kept constant. What we need to do now is to see what happens when we change the mass, because if we change the mass, we change the inertia, and it's got to have an effect. What do you predict? Now we're ready to investigate the relationship between mass and acceleration. The first experiment is set up exactly as before. The applied force is 100 newtons, and as you can see here, the mass of the filing cabinet is 500 kilograms. Let's go. Velocity increasing slowly, big inertia, 500 kilograms. Pause it there, and I'm going to half the mass. So go over here, and 250 kilograms. Continue. Pause again. The velocity very definitely is increasing faster than it was before. Let's go over and half the mass again. And restart. And there you can see the velocity increase faster yet again. So the acceleration time graph should look like this. Yes. The force was kept constant now, remember, so everything you see changing on the acceleration time graph was due to the change in mass. Let's replay it. 0.2 meters per second acceleration, and now we half the mass, and the acceleration doubles. And then we half the mass again, and the acceleration doubles again. That's an inversely proportional relationship. Again, beautifully simple. We double the mass and the acceleration halves. So there is a very simple relationship between force and acceleration and mass and acceleration. Let's put them together and see if we can make sense of the whole thing. We write acceleration is proportional to the unbalanced force like this. And acceleration is proportional to the inverse of m, like this. We can put those two together. If we choose our unit of force, the Newton, carefully, that makes this relationship boil down very simply, and we end up with this equation, the second most famous equation in physics. F equals ma is Newton's second law of motion. Does it only apply in the ice lab? Well, no, it doesn't. Here I am back in the ordinary lab with the wooden floors. Let me remind you what happens when I start to push. The forces are all balanced. Newton's first law says that the crate will stay doing what it's doing, and it does. So let's push a bit harder. As soon as we had an unbalanced force, the crate started to move exactly in line with Newton's second law. But does it obey the equation? Let's have a closer look. Now we're ready to analyse the situation in more detail. You can see that I'm pushing hard now. There is an unbalanced force, let's emphasise that. The green arrow has appeared, and that is the sum of the total forces acting on the crate. It is solely responsible for what you're going to see as soon as I press the start button. Predict what the three graphs will look like, and then we'll start. Here we go. So let's look at a replay. I'm going to remove the applied force and just concentrate on the total force, the green arrow. Here we go. Pause it there. What do we see? Over here you can see that the mass of the crate was 100 kilograms and the acceleration was 4.06 meters per second. The total force, therefore, should be the mass times the acceleration, 100 times 4.06, that is 406 newtons. That's exactly what the sum of forces is given in this box here. F equals ma works. Of course, there is one small problem here, and that is that we are using a computer simulation which has been taught Newton's laws. What we really need to do now is to go out into the laboratory and try real experiments with real crates and real trolleys to find out exactly how F equals ma stands up to examination in the real world. And we'll do that in the next video. Finally, let me introduce you to the third law. This is the one that everybody remembers. For every action force, there is an equal but opposite reaction force. What does that mean? Basically, forces always come in pairs. Let me show you. Here I am pressing against the wall with a force Fa. This is the action force. There must be an equal and opposite reaction force. How do you think I can represent that on the diagram? This force is supplied by the wall. I press on the wall and the wall presses on me. It's important to understand that the action and reaction forces always act on different objects. You might say, why have I not mentioned this earlier? The fact is that I didn't need to. Let me illustrate this with an example. The wall is pushing on me. Why am I not moving? Well, the answer is that this is not the only force acting on me, of course. Here's the friction. The forces acting on me are balanced, so Newton's first law says that I will remain at rest, and I do. Notice that I've dropped the action force from the picture. The fact that I was pressing against the wall is irrelevant. If you want to know what's happening to me, you only need to consider the forces that are acting directly on me. What would happen if I jump round to the other side of the wall, where we have ice? There's no friction. Let's try it. I'll pause the simulation first so we have time to think. OK, when I release the pause button, the forces will be applied. What will happen? Here goes. I accelerated away from the wall as predicted by Newton's second law. But as soon as I stopped pushing, I travelled along the ice with constant velocity. Newton's first law. We've completed our journey through Newton's three laws, so we need to test them out in the lab. And we need to practice doing the calculations. So maybe I'll see you in the next video. Bye for now.